Welcome to Practice number 126, and today we're talking about different flow control devices on cars, especially around cars that are cornering, and we're looking at movable aerodynamic elements as well to some extent. This is going to be a two-part podcast series because there's a lot to go through. In this first part, we're going to go through the CFD mostly and a lot of flow control devices investigated in a CFD situation. In the second part of the podcast, we'll finish off that little bit because there is quite a lot there, but then we'll also look at the actual real-world like on the road testing of some of these devices, including a wing which is at an angle, and that's for cornering purposes. So to look at this, we're going to look at a paper called Influence of the Car Movable Aerodynamic Elements of Fast Road Car Cornering. This is an open access paper which you can find in the link in the description. And let's get on with the podcast. So this, for example, this picture here, if you listen to this on Spotify or Google Plays or whatever, you can look at the video on Spotify and or YouTube. On YouTube, we have other goodies as well, which you can find and enjoy there. But looking at the type of things that this paper is covering, in the second podcast, we'll look at this sort of, and in a bit in this podcast as well, this wing at a different angle. So you can see these hydraulic parts here, moving the different parts of the wing up and down to create a angle for cornering. And this is on a kind of a supercar, kind of a racing car format with like diffusers and etc. So they say this paper deals with the study of the effect of asymmetric flows around a sports car with several moving aerodynamic elements characterized by local asymmetric flow structures. So in other words, a car moving around corners and the flow control devices are creating asymmetric structures, which is quite unusual for a car. Usually they're quite symmetrical. At the very least, they are bluff, so they do have this periodic symmetry to them. If you were to average them out over time, it would look symmetric the wake. So let's move on to the materials and methods and the objective of the study. So the objective of the activities presented in this paper was a prototype of an Arinera Hisari supercar. I haven't really heard of this one before, but it looks very supercar-like. Like it looks like kind of like a Ferrari 458/Lamborghini Gallardo, something like cross between those two. So it's very supercar looking. The simulation domain and calculation method is very interesting. So the numerical simulation was conducted on a real scale object in the orthogonal wall and curve design areas with dimensions shown in figures 3 and 4. So what does this mean? They got a car and they scale it down to, it looks like about a 1:5 model, because the entire simulation, maybe a bit less, maybe even like 1:6, 1:7, because the entire simulation domain is only 5 meters long and the car itself takes up like maybe 10% of that, maybe a bit more. So it's like a 1:6, 1:7, 1:8 model kind of thing. And interestingly, they have two different types of domains. They have a curved one, which is really cool. You don't really see this very often. Then they have a straight one where they apply an MRF, and we'll go through these two different ones now. So in figures 3 and 4, for the analysis of the vehicle motion on a curved track, the natural geometry of the calculation domain is the curved area shown in figure 3. So you can see if you look at like any of these walls, they curve a little bit and the car is in the middle here. However, curved motion calculations were also performed in the orthogonal area. So in other words, a typical CFD domain where you have literally just a straight box, like a rectangular box, and you put your object in the middle here. So they're straight lines, so they're not curved here like the other one. So they have two different ways here. And for this straight line one, what they did was they did some pretty fancy mathematics to kind of approximate cornering, and we'll cover this now as well. So in both cases, a slightly modified moving reference frame, MRF technique, was used to simulate the car's motion. So what is the moving reference frame to begin with? Well, it's often used on symmetrical bodies. Let's say you have it's often like, let's say, a wheel. So we have a wheel, and then inside we have the spokes, obviously. This is not a great drawing, but I assume that this is a typical wheel. What we'll do is we'll specify this volume here, and we'll say, okay, all the cells in this volume are moving in this direction, this clockwise direction, for example, or counterclockwise or whatever, with a certain rotational velocity. And obviously, the further away you get from the center of the axis, like the axis of rotation, the faster the tangential velocity is of these cells. And you say, okay, these cells are moving with this velocity, but they don't actually move. You just say there's this velocity in this direction, and you calculate that into the velocity that you're calculating. That's an MRF, moving reference frame. They use the modified one because this is not a closed shape. So usually you have to use this on a axisymmetric shape, so a wheel or a turbine stage or whatever. this is not actually symmetric, obviously, it's a domain. So for the arc domain, the boundary conditions, this technique of MRFs involves using a stationary grid and superimposing the conditions of a moving reference system representing a moving vehicle on the entire computational domain. What does this mean? So for this square domain, like this rectangular domain with no curved sides, what they're saying is, okay, we're just going to say that there's like this kind of motion going along there. And we're going to say all these cells, depending on how far away you are from the center of rotation, has a different tangential velocity moving in this circular motion. So it is quite an ingenious way of using the MRF, and it's quite tricky to get that to work in CFD. So they did quite a nice job here doing that. They move on and say, for the arc domain, so the one where they actually curved the domain, the boundary conditions were a velocity inlet on the wall in front of the vehicle, as expected, a symmetric condition on the sides and top walls, and a pressure outlet condition on the wall behind the vehicle. For the cuboid domain, the velocity inlet condition was applied on the face and side walls, the symmetry condition on the top wall, and the pressure outlet condition on the wall behind the car. With the MRF technique and such given boundary conditions, a situation was simulated in which the vehicle moves along a curved track with a given velocity relative to the still air and a stationary roadway. The rotation of the wheels was simulated by superimposing on the wheel surfaces the velocity resulting from the rotation. So what I can tell from that description, for the wheels, I think they're using a rotating wall condition. So what this does is you literally just have whatever object you want to rotate, let's say your wheel, and you say, okay, on this surface, we just have this rotation occurring on the surface, not the cell volume. So in this MRF situation, you have like the entire volume surrounding the wheel. On this, you're just looking at the surface of the rotating wall condition. That's the difference. The rotating wall condition is significantly cheaper to do computationally, and was before the MRF approach. Both of them are somewhat outdated these days. The sliding mesh is often the next best thing, but rotating walls and MRFs are good in certain situations. If you take account of the variables that they don't handle very well and you account for them, then MRFs are fine and rotating walls are fine. So figure 5 shows the various meshes that were used. The most common technique used was the Overset Mesh technique, which allowed for the effective changes of additional aerodynamic elements. So what is this? So far in this podcast, we've talked quite a lot about CFD methods, which it's good to know. So this Overset Mesh technique, what is this? Let's say we have your object. It can be any object. Let's say it's a rock with another rock on top. And this second rock is moving around with respect to the first rock. Well, regular meshes can't really handle this very well. So what we do is we actually make a secondary mesh around just this second rock, and we have the entire mesh around the first rock plus the second rock. And what we do, we move this rock with this mesh, and all the values that are calculated on this mesh then get transported onto the global mesh, so this first big mesh. And so that means we can move this entire object around and still simulate our domain, because the values calculated on this mesh are still calculated wherever it is in this bigger domain, and these values are just imprinted onto this larger domain, and we can then use these values to understand how the entire flow in the entire domain is. This is what an overset mesh is. The great thing about overset meshes is that you can have as many as you like. So you can have another rock around here if you like, and have another overset mesh, and just have them moving around. So that's very powerful. They are very expensive too, but in this particular case, because they have moving objects, that's a very cheap way of doing it, instead of trying to find some sort of like quasi-static way of moving elements and remeshing and resimulating. That would be much harder to do, whereas using an overset mesh is far easier. They say individual meshes for the car body and additional aerodynamic elements were generated and later superimposed on each other, as I mentioned. Used overset mesh techniques connects the fluid zones by exchanging the interpolated cell data in the overlapping regions. That's what I mentioned earlier, where you measure or you calculate the data that you need for each overset mesh, then you impress that onto the global domain. Due to this process, the additional element meshes could be freely translated and rotated in the computational domain. Considering the number of simulations, the overset mesh method significantly reduced model preparation time. So in figure 5, we see the mesh generally set up here. Now in figure 6, they talk about the boundary layer mesh that was designed to fit the Wolf function approach. What does this mean? What this means is, so let me get rid of all these drawings and do some new drawings. So if we have a wall, for example, this is, let's say, the ground, and we have our mesh coming in. Let's say it looks like this. Oops. Okay, again, not a great drawing, but bear with me. Okay, so the distance between this first cell is, like the height of this first cell and the second cell, and so on, are very important. This is determining how well the boundary layer is resolved. The boundary layer is very important. Using wall functions allows us to have a thicker first cell, so the first cell height is greater, and not compromise much on accuracy. So what we do is we use empirical functions, which means we get data from real life and even DNS, for example, so like very good CFD, and then we figure out equations that approximate the boundary layers under certain conditions. We then use those equations to on poorer quality CFD to be able to use a thicker cell height, first cell height, which means we can reduce the number of cells and still get a good result, hopefully. Now, there is a limit to this where if you have a too thick a cell height, first cell height, then these equations start to break down because you start to get just complicated flows that don't really, that are very particular to what we're looking at. So what they're doing here is they want to get a y plus value, which indicates this first cell height compared to the boundary layer situation below a certain amount, but not so small that we then have to have so many cells. And then this fairly coarse first layer height can be made up for with wall functions, with these empirical equations, which help fill in these gaps. So the question is, what should the y plus be? This y plus value tells us how resolved the boundary layer mesh will be. A y plus value of 1 or less is often ideal, but that means we need to have more cells. If we have a boundary layer y plus of greater than 1, then that means we can use fewer cells, but we run the risk of being less accurate. And the greater this y plus value is, the worse our result probably would be. So for example, on this situation here, figure 6, much of the car has a y plus of like 1 or less perhaps, which is very good. But some of the car has a y plus up to like 60, 70, 80. That's not ideal. You would probably want to refine the mesh here a bit more, but they're using the realizable K epsilon approach, so this is a particular terminus modeling approach, RKE, realizable K epsilon. You can look this up on Google if you like. And what this does is it's like part of the K epsilon family, and you can get a y plus value of like 30, and it's generally okay. Y plus and the K epsilon approach in general is not great. So having y plus of 30 is not going to make it much worse. Having y plus of like 100 or 200 is then a problem. But most of this car is like 30 or below, or 40 or below, so that's okay. So they talk about the grid independent study, which they did perform here quite nicely, and they showed that they said the numerical model was validated by comparing the results of wind tunnel tests of one of the versions of the prototype, the numerical model of the racing version of the prototype car with different cooling system designs and geometries and different engine air intakes and large front splitters and canards, and a large rear wing was verified compared with experimental data obtained in the Myra wind tunnel. What does this mean? So they went into the Myra wind tunnel, which is a wind tunnel in the UK. It's quite a famous one for automotive aerodynamics. And although I guess in the 80s and 90s was like its heyday, and they did some experiments on this very car, but with a slightly different body kit effectively. They have different flow control devices, the heights, and even like the canards, for example, if you look on figure 8 in the CFD, you can see on the very sides where my cursor is now, these two little like fins, and they're canards. They're not seen on the car in the wind tunnel. So there are some differences between them. One of the most noticeable ones, or one of the most important ones, is the cooling system design. So I'm not sure if there is cooling, like the cooling flow on the CFD, but there definitely is on the experimental one. And that can change the drag coefficient by 20, 30 counts. So they say here that a compliance of drag coefficient of 3.8% and a lift coefficient of 6.5% was obtained. So in other words, a difference between the drag found in the CFD and the experiments with 3.8%, and for the lift coefficient, 6.5%. So there is quite a big difference there that's to be expected based on the different geometries. They say calculations show slightly less drag and slightly higher aerodynamic downforce compared to the experiment. For comparison, in a study by Zhang and others, experimental results were compared with numerical simulation results of a highly detailed sedan vehicle model with different terminus models. The most popular RANS terminus models, so realizable K-epsilon, Abe, Kondo, Nagano, K, Omega SST, and V2F, and hybrid models SST, DDES, IDDES, observing differences in the calculated drag coefficients ranging from 1.3 to 30.8%. So in other words, they've gone into the experimental wind tunnel, they've looked at the drag that they're getting and the lifts that they're getting errors of about 3.8% to 6.5%. They're also looking at the CFD that they're using, whether they're using RANS with whatever terminus model they're using, plus more high fidelity ones, DDES, IDDES. I should probably cover these ones in a second. And they wanted to see what is the best approach for CFD. These researchers, Zhang and others, found that the RANS approach with the RKE model, so their realizable K-epsilon model for their terminus modeling, gave the best results. That is surprising for a couple of reasons. I'll get into that in a second once I've discussed what DDES is and IDDES are. But yeah, that's probably not something to be trusted. So what is DDES and IDDES? First of all, RANS. We've talked about RANS a lot on the podcast and even in our other videos as well. So RANS is the most, like the least computationally expensive regular CFD, like Navier-Stokes solver CFD approach. And there are a bunch of different terminus models to be able to model the terminus that's forming in the domain. We use realizable K-epsilon, SST, K-omega, K-epsilon, Spell-Dalmaris, lots of other ones. And generally speaking, anything to do with RANS shouldn't be as accurate as anything that's high fidelity. DDES and IDDES are high fidelity. So what is DDES and IDDES? They come from the DES family. This stands for detached eddy simulations. So what this means is it's an amalgamation of LES and RANS. So LES is large eddy simulation, which means that we have a very, very fine mesh. And this means that we are resolving effectively most of the eddies with the energy. So obviously all eddies have energy, but generally speaking, the larger eddies have the most energy. So we want to capture most of that energy as possible. That's what LES does. Once we get to a very fine level, we then start to get to what's called the subgrid scale. And that's where we start to have to use equations to kind of figure out how much energy the very small eddies have. And the reason why we don't resolve those properly with our mesh is because we need to have a very fine mesh to be able to do that. And to do that, we'll start to verge on like DNS kind of meshes, which is impossible to do at the moment based on our computational abilities. So LES is the next step up, the next full step up from RANS in terms of accuracy. It measures it, you accurately simulate the large eddies, as the name suggests. DES is kind of halfway between RANS and LES. What happens is we have like the RANS modeling near the wall. So when we are in the boundary layer, we'll use a RANS approach. But when we are further away from the boundary layer, or even partly inside the boundary layer, we'll use a LES approach. So we'll have this meshing between the two. That's DES. DDES and IDDES stand for delayed detached eddy simulation and improved delayed detached eddy simulation. It's very heavily in semantics, but effectively what this does is it staggers, like you have to go further away from the wall for LES to kick in. And there's like these things called shielding, which is like when you have certain properties that are triggered, LES will not trigger and you still stay in the RANS. Why do we do this? Because there can be problems between matching the LES and the RANS halves of the simulation. If we are still inside the boundary layer and we go from RANS, let's say we have RANS here, and then we go to LES or LES here, there may be some properties which will then just start to trigger errors in the data that we're calculating between these two cells, which will then result in the simulation crashing. So DDES and IDDES allow us to stagger that transition from RANS to LES. So that's what these are. So that's LES, DES, IDDES in a nutshell. It's very complicated, and I wouldn't blame you if your head's kind of spinning and going, what's all this? If you have questions about it, let me know in the comments below and I can answer them. But let's move on now, because that's probably a little bit more than we should have spent on this podcast on these. But the moral of the story is the DDS and IDDS simulations should have given better results than the RAN simulations. Nevertheless, these researchers are going with the RAN's simulations based on some literature that they found proving otherwise, which I would question that literature. But anyway, let's move on. They're using RANs with the RKE model. Now let's move on to the actual results that they found. So the performance analysis of selected additional aerodynamic elements. So one is the addition of a booster plate for a sports car. What is a booster plate? This is really cool. So imagine the back wing of a car, and you have the boot, so the trunk, and then you have the wing coming up behind it. Now that's going to be producing quite a lot of downforce, which is nice. But there's also an additional thing called a booster plate, which is like effectively like a spoiler at the back that pops up at an angle, and all the flow comes into the spoiler just underneath of the wing and just gets pushed straight up. And this results in a greater downforce, but also a greater wake behind you and a greater drag, generally speaking. And this is really cool because there are some benefits to it. In figure 9, we see a view of the retracted spoiler with a plate just below it. So the wing has been popped down and this plate is below it. In figures 10 and 11, we can see it a bit better. So you can see here at different angles, this booster plate. They say in one version of the car, a section of the upper body was raised and rotated to act as a spoiler. Several versions of the booster plate were analyzed and are shown in figures 9, 10, and 11. In figure 12, the results of this booster plate at different angles of attack plus the wing are shown. So for each spoiler angle, the plate is also rotated so that the flow is properly directed under the spoiler. Examples of the spoiler and booster plate positions are shown in figure 10, so I showed that there. The aerodynamic characteristics of the drag and lift coefficients of the car with the spoiler and with the addition of the booster plate as a function of the spoiler setting angle are shown in figure 12. In the diagram of figure 12, the angle specified as 10 degrees corresponds to the spoiler operating setting, providing minimum aerodynamic drag, while the setting angle of 55 degrees corresponds to generating maximum aerodynamic drag during braking, which is good because you want to throw off as much drag, as much speed as possible in the corners to be able to slow down quickly and go around them and speed it back up. And you can also go into the corners faster because you can brake quicker, which can increase your overall speed around the track. They say, the most remarkable differences occur for a 30-degree position angle, and for this case, the visualizations are shown down here. We'll discuss those in a second. Let's move back to the graphs for the second now. The maximum difference in the downforce coefficients between the two cases was 0.14. From the graphs, it can be also seen that a similar drag coefficient as for the pure spoiler during braking occurs for the spoiler with a booster plate at an angle of attack of 20 degrees or less. So in other words, when you have an angle of attack of 20 degrees or less, the drag coefficient between just the spoiler and the booster plate are quite similar. So there's not much happening there, although there is a little bit of an increase with the booster plate, but not as much as you'd expect. They say, so here we can see that with the booster plate, as we get to like a 35-degree angle of attack, the lift is increasing by, or the downforce, I should say, is increasing by like 20%, or more than that, sorry, probably about 40%. So that's a really good increase. And the drag coefficient is only increasing by about 10%. So that's dramatically increasing the efficiency of this car. We're getting a massive increase in the downforce and not much of a drag penalty. So that's quite nice. Looking at the CFD of this, so the wake surveys, we can see that the booster plate in this figure here, you can see my cursor, it increases the wake quite a lot. So here where there's no booster plate, you can see the flow comes in, it's quite fast, still comes through, there's still a wake, but it's not as big as with this booster plate. So that's going to increase the drag. Also, because the flow is being pushed up a little bit more, that's obviously going to increase the downforce. So what about a spoiler with a gurney plate? A gurney flap, sorry, which is 3 centimeters high. So a gurney flap is considered a simple and effective solution for obtaining additional lift or downforce if the increase in aerodynamic drag of the solution can be accepted. So what is a gurney flap? A gurney flap is, let's say we have a wing here. It's this little thing at the back that just pops down. So it's like just this little flap that comes down. And this greatly improves the performance of a wing often. And here they say, extending the gurney flap resulted in changes in the lift coefficient from minus 0.3 to minus 0.49. So this tiny little gurney flap of 3 centimeters tall increased the downforce by 60%. What about the drag? Well, the drag increased as we expect, but not that much. It only increased from 0.43 to 0.51. So it's only like a 20% increase. So we get a 60% increase in the downforce with only a 20% drag penalty. That's freaking awesome for how small this gurney flap is. And if you look at figure 16, we can see why this gurney flap is so effective. We can see that, okay, the wake is bigger here, but if you look at the pressure on the pressure surface of the spoiler, the pressure is so much higher, which means that we're going to be getting a lot more downforce because the pressure difference between the top surface and the bottom surface is greater, and it's in the direction of going down. So we get this greater downforce. That's why these gurney flaps are so effective, and the drag penalty is not that bad. So what about a splitter? We've talked about like spoilers now and flaps. Let's talk about splitter plates. Splitter plates are the plates that you see on the front of a vehicle underneath, and that's pretty much to like segregate the flow that's going underneath and make it a bit cleaner. Let's talk about how this affected the aerodynamics of the car. So another additional element analyzed with the splitter located under the front part of the car body. The geometry shown in figure 2 was taken as the initial geometry without the rear spoiler and front splitter plate with neutral aerodynamic characteristics. Parameters presented in table 1 represent the coefficients of the aerodynamic forces and moments. The small lift coefficient of the body is mainly due to the action of the diffusers under the rear part of the body. Due to the high sensitivity of the flow in the diffuser channels to the changes in the body's distance from the ground, optimization of the diffuser channels was not addressed. Let's talk about this. So first of all, with and without the spoiler, the parameters of the car without the spoiler and without the splitter plate, the drag coefficient was 0.3. The lift was positive, it was 0.0145, sorry. And what they're saying here is because the lift that is the downforce that is being produced by a car is often, the majority of it is often produced by the diffuser and the underbody, because the splitter plate is here and the height of the car is not really investigated, we can't really optimize this car to produce as much downforce as possible. If you look at a car, often they just look like flying wings. You can see here, the curve on top and the flat underbody is effectively just a cambered wing going along. That's going to be producing a lot of lift. The way that we get around that is by lowering the car to the surface, and we sort of restrict how much fluid is going in underneath. This results in like Venturi effect with the diffuser as well, and this then results in a low pressure, which then can overcome that natural tendency to produce lift and actually produce downforce. They didn't look into this at the moment, but that is where the diffuser, the splitter plate, and the underbody come into it. Let's move on to the separated wing. So instead of the initially planned movable rear part of the body having more the character of a spoiler than a wing, during the numerical analysis, a modified airfoil was used with an additional element above the end of the airfoil. So in other words, a 2-element airfoil. We have one element here and the other element behind. The other element is effectively just a flat plate. They say figure 18 shows the pressure distributions on the upper and lower surfaces of the airfoil, 4 angles of attack, and the values of the aerodynamic force coefficients in the configuration with an inactive gurney flap. So in other words, no gurney flap. Up to an angle of attack of 5 degrees, no flow detachment is observed. At angles of attack of 10 and 15 degrees, there is a large flow detachment area on the airfoil's underside. So in other words, the suction side is stalling. What does this mean? Well, when we have the splitter, like the spoiler, at 0 degree angle of attack, the lift and drag that we get are a certain value. We increase the angle of attack by only 5 degrees. The drag increases pretty bad, like it's like 30% increase. The lift only increases by about 15%. So we're getting a massive drag penalty for how much downforce we are producing. Is that a bad thing? Not necessarily, depending on what we want to do with the car. If we're going around corners, then that might be acceptable because the increase in downforce is good to get around the corners, and the increase in drag also helps us decelerate. As we go to high angles of attack, the drag skyrockets. It goes up to like double, and the lift coefficient doesn't really change very much, if anything. So we're getting a lot more drag, which will help with braking, but we don't really get any more downforce, which won't really help the car go around the corners much faster. Also, if we are going slower, we lose lift or downforce as well, because downforce is proportional to the velocity squared. So that's also a potential problem there. But overall, it shows just how sensitive this wing is to different angles of attack. Just increasing by a few degrees greatly reduces its performance. So that's all we're going to cover in this podcast today. In this next podcast, we're going to go through the rest of the CFD, which is a separated wing as supportive plate, plus tilted wings, plus real-world on-track experiments. And they have like accelerations and all that. So far, we've covered the effect of a gurney flap, which was amazing. We've covered the effect of a booster plate, which we don't really see too often, and that's pretty cool as well. And also how to simulate this CFD, which they've looked at two different approaches with the curved track and a straight track. So that's in this podcast. Make sure to like, subscribe. And if you want to get better at CFD yourself like this and or theory, check out our course in the description. And if you want to make your experiments 2% more accurate, check out the Atmosphere Hawk. Essentially, when you make to accurately measure the density of air. The reason why this is important is because the density of air changes every day by 2 to 4%. And between days, weeks, months, seasons, even more, 15% is normal. So if you do your experiments on different days, or even on the same day, but you don't take into account the density of air, you're going to have that error in your data and you don't even know it. That's a major problem because when you're trying to find trends, you're obviously going to be getting this error that's just corrupting your data and you don't know why. What's more, we often use experimental data to validate CFD like I did here. And if you're trying to validate your CFD and you have the wrong density of air, which if you haven't measured density of air, then you will have the wrong density of air because you have assumed something which is not true, then trying to validate that CFD is going to be erroneous. The Atmosphere Hawk gets rid of that error for you, so you can then trust your experimental data and thereby trust your validation process and your CFD. The Atmosphere Hawk is a really good instrument. It's very easy to use. Check that out. Links, and I'll see you in the next podcast. Peace out, amigos.